So the idea with angular momentum is pretty much the same thing as the linear momentum, but not the analogous in rotational motion. If you remember, we said there is two types of motion. One is translational motion, the other type of motion is rotational. And every motion that we observe in nature can be described as either one of those purely or a combination of both, right? And so we've seen all the physics solved in kinematics for 1D and 2D, but basically in translational motion, and then we saw everything for rotational with angular position, angular velocity, and angular acceleration. Then we introduced the idea of forces, and then we saw force is equal to mass times acceleration, and then we introduced the analogous of that in the case of circular motion, that we said for circular motions, accelerations, that's an increase on the angular velocity, are not produced because of forces, but because of torques, right? The torque being the angular equivalent or the angular analogous of the force in translational motion. So how are we going to define angular momentum is precisely the same way. So if we said force is equal to mass times acceleration, and remember this was for translational motion, now we're going to be saying that torque it's equal to what? Now we don't have mass, now we have inertia, and we don't have linear acceleration, we have angular acceleration. But what's angular acceleration? Well, that's just angular acceleration is just the change in omega over the time it takes to do that change. And so we can redistribute and say that tau, which is the torque times the change in time, it's equal to inertia times delta omega. And that's inertia, omega minus initial omega. And so we can rewrite again this, and we can identify this. So how we start from here, we're going to say that torque times the amount of time, that's going to be the impulse. In this case, we can call this rotational impulse, which is equivalent to when we were talking about the linear impulse in the case of translational motion, where we said, well, rotational motion has an impulse which is equal to F times delta t. Now, we're not going to be, these are vectors, and we're not going to be considering torque as a vector in physics 2053. The only thing the torque is going to have is positive or negative direction, depending whether the acceleration is positive or negative, but nothing more. So we're not going to have a vector description of torque, although technically we should. And then we're going to see the right-hand side, we can write it as I times omega minus I times omega 0. So if we define I times omega as the angular momentum, and we're going to call that L, then we're going to see that this is actually the change in angular momentum, or rather, step by step, final angular momentum minus initial angular momentum, in other words, the change in momentum. And so we're going to find exactly the same thing we said before, or the equivalent thing that we said before. Before we said that any change in linear momentum is the result of an impulse. Now we're going to say that any change in the angular momentum is the result of what? Of a rotational impulse. So every time that we put in a box an object spinning and we close it, we expect to find the object is spinning the same way in the absence of any external impulse. And that means that the amount of rotational motion, we were discussing that linear momentum can be understood as the amount of motion, translational motion. Now we're going to understand angular momentum as the amount of momentum rotationally. Again, important, just remember the torque is defined as the force. So if you have a circular motion, what accelerates this object, what produces an alpha, is not the centripetal force responsible for curving the trajectory, right? It's not the acceleration c. Remember that in circular motion, acceleration is centripetal acceleration and tangential acceleration, where the centripetal is responsible for the direction and the tangential is responsible for speeding up. So actually, when it speeds up, the motion is a tangential acceleration, meaning applying a force in this direction, a tangential force. Therefore, the torque actually is the tangential force times r, where r is the distance from the point of where you apply the force to the axis on which the object is rotating. So this, just remember that in this case we're using the rotational for a rotational motion. Torque, which is the equivalent of the force, is not the centripetal force that needs to be there, otherwise there will be no circular motion, but rather it is the force responsible for accelerating that circular motion, and that force is for speeding up. That is what's related to alpha, the angular angular acceleration, So this is just a quick review. Let's see how we apply it in problems. The idea is going to be exactly the same. We will write this, we will define our system clearly, we will observe how much rotational motion the object has at the moment, then we will wait, we will analyze how much rotational moment has at the end, and then we will see, are there any impulses coming from outside, are there any torques responsible for rotational impulse? If there are none, then the same amount of rotational motion needs to be at the beginning and at the end, and we can use that accounting tool to solve problems. Let's see some examples. So problem number 1 in discussions, we said there is a propeller of an airplane, typically let's say something like this, right? Okay, and the idea here, excuse me, is that this propeller has a mass of 70 kilograms and a radius of gyration of let's say that the radius here is 75 centimeters. Now, of course, we immediately know that's 0.75 meters, and it's good practice, again, as always, convert every unit into international system to avoid issues. So we want to know first what is the moment of inertia. So what is the moment of inertia of this? Unless it's otherwise told, because we're not using calculus, we cannot determine what is the moment of inertia of this particular geometry, which you would have to integrate, and probably integrate 1 and multiply times 3. But basically, what we're going to assume is that all the mass, it is concentrated, let's say, at the tip, which of course is not a reasonable thing, but anyway. And then assume it's just simply a sphere rotating with the entire mass on outside. And so we're going to take that the formula is just simply the mass times r squared. Unless otherwise told, you can assume this is the moment of inertia, because anyway, qualitatively, it's going to give you a good idea. The inertia increases, inertia, again, rotational inertia, meaning the opposition to the change in the rotational motion, increases the farther away you're from the axis of rotation, which of course in the case of the propeller is just the center, excuse me, the center, and of course proportional to the mass. This is the same as in linear momentum, right? That's a property inner to the object in question, right? So rotational inertia has these two components, the one which is proper to the object, which will be mass, which is what we call translational inertia, on inertia and translational motion, but also has a component that is geometrical, is how far that is from the axis of rotation. Anyway, so we're going to use that number, and so we can just simply say that inertia is equal to the mass of this object, which is 70 kilograms times 0.75 times squared. And if we make these numbers, we find that this is about 39. And now it will be kilograms per meter squared. Okay? So that will be the moment of inertia of this propeller. And again, the assumption here is that all the mass is concentrated out the outside, it's just simply rotating, which of course is not a good approximation, but at least qualitatively is going to give us an idea, right? Okay, so the next question then is, once we have determined the angular, the moment of rotation, we ask how much torque is required, such as the angular acceleration is 4 revolutions per square second, right? Square second, because it's an acceleration. So as always, we need to go first of all from revolutions to radians per second, or in this case radians per square second. So how do we do that? We remember that 1 revolution is 2 pi radians. So that means that 4 times 2 pi radians per square second, which of course is 8 pi radians per square second, right? That's the acceleration that we want to find. And now the question is, how much torque do I need? Well, that's basically saying that I'm going to apply a torque that is going to produce an acceleration that is proportional to the rotational inertia. Therefore, to produce that acceleration, we need to multiply, to produce that acceleration for this particular inertia we just found, we just need to multiply the numbers. So that's going to be equal to 39 times 8 pi. And if we do that, so we're going to find that it's about 1,000 newtons per meter. So again, the torque is giving us newtons per meter. We knew that. You can work out the answer, but basically you have here kilograms per meter square divided per per square second. We're going to have newtons and then times meters, because you have meters square with meters again, right? So okay, anyway, how much torque do you need? 1,000 newtons or 1 kilonewton, right? We could say this is about 1 kilonewton per meter. But here, if I make a propeller that is bigger, let's say that the mass is rotating towards the outside, I'm going to need a larger torque. If I make it smaller, it's going to require lesser torque. And don't forget, at the end of the day, a torque is actually a force that is being applied tangential, right? So tangential force on the propeller. If I want to make this propeller accelerate, I have to kick it like this, right? I cannot just push there because the propeller doesn't move. If you push inwards, the propeller doesn't speed up. How does it speed up? Again, from the point of view of rotational motion, with tangential force. So the torque is responsible for that acceleration in rotational motion. Let's see more problems. So that's the problem number 2 now. It says there's a grinder wheel, and the wheel has a radius of rotation of 8 centimeters, and it goes uniformly to rest from 1,400 revolutions per minute to a final velocity of rest, right? It goes to rest in a time of 35 seconds, and the mass is 0.9 kilograms, right? And then the question is, how large is the friction torque that slows its motion? Again, torque is going to be the result of a tangential force, but tangential force is not a new type of force, it's just a directional force. In the sense, it's telling us this force acts tangential to the motion. It means it acts on the direction of the motion, but that force might be of a different nature. It could be normal, it could be friction, it could be tension, whatever it is, right? If this is the wheel and I put a string and I pull from the string, this thing is going to rotate, right? That's going to be a tangential force that is produced by a tension force, if you wish. Well, yeah, you could say that, or you could say this ultimately friction, because anyway, that's just a matter of approximation. But the idea here is that tangential force is just telling us it's acting tangential, centripetal force is telling us it's acting towards the center, right? So it's not a new nature of force, or it's not even a new phenomenological thing. It's just a description, let's say, from the point of view of the direction in which the force is applying. Another question, of course, is how large is that friction force is going to produce a torque. How large is that torque? And in this case, we're provided the inertia moment, which for this particular geometry we're told is of a disk, which is 1/2 of mr squared. Okay, so this we see a first variation. Before we were saying mr squared for a sphere with an axis, now for a disk is 1/2 of that, right? We're not going to determine these things, we cannot, we need differential calculus, we don't use that in physics 2053, but certainly if it's some other geometry, they're going to give you the value that you can use it. Okay. So let's start. There's ways that we could do this. We could just use conservation of angular momentum and say, well, this object is moving at the beginning, but it's not moving at the end. It's losing momentum. If it's losing momentum, why is that? Well, it's losing momentum because there's an external interference. There's an external interaction acting. There's an external impulse. And what produces the impulse? The torque. So you can do it either way. Let's start by analyzing that torque definition is just inertia times alpha. And how much is alpha? Well, alpha is the change in omega over t. How much is the change in omega? That's going to be 0, which is the initial minus final, minus beginning, which is, before we do this, before we do that, this is in revolutions per minute. So first of all, we need to convert that into radians per second, or the entire thing is going to go bad. So let's start from 1400 revolutions per minute. We remember that the revolution is 2 pi in 60 seconds. So now this converts into radians per second. So it's going to be 1400 divided by 60 times 2 pi radians per second, right? And so we can write that for a value, it's equal to, that is equal to 146 radians per second. So 146 radians per second. And now we can use the formula, which is that the change in omega over time defines the angular acceleration. How much angular acceleration is this? Well, it will be an angular deceleration. So what do we expect the sign to be? That we expect the sign to be negative. So we replace the numbers and we divide by the time. So that's going to be 146 divided by 35, which is going to be about 4, no? Something like that. About 4 what? Radians per square second. So that calculates the acceleration. What about inertia? Well, inertia is given by 1/2 of the mass times r squared. So let's replace. Mass is 0.9, and the radius is 8, so it's 0.08 squared, right? Which is 8 10 to the minus 2. That's why notational scientific notation is much more comfortable, because there's going to be 64 10 to the minus 4. So it's much easier to work with that. But anyway, so if we calculate that number, we're going to see that the result of that is about 2.9 10 to the minus 3 kilograms per meter squared, right? And then from those numbers, we can finally determine what is the torque. Well, torque is I times alpha, so it's going to be 2.9 10 to the minus 3 times 4 radians per second, and that's going to be like 11.6, right? 11.6 10 to the minus 3 newtons per meter. And and I forgot, by the way, we forgot the sign. So here we're going to need to add negative 4, and so this is going to be negative 11.6 10 to the minus 3 newtons, or 11.6 millinewtons per meter, something like that if you wish, or newtons per millimeter. Yeah, you could use any of those options. So again, we have calculated torque. What's interesting here is that torque is negative. When torque is positive, torque is producing an increase in the amount of motion. Why? Because if torque is positive, if torque is larger than 0, inertia cannot be smaller than 0. Why not? Because you have the radius which is positive and the mass which is positive is always going to be positive. So if torque is larger than 0, it is because alpha is larger than 0. If torque is smaller than 0, meaning negative, it is because alpha is smaller than 0. Whatever the sign of torque comes from alpha, and alpha is the acceleration. So whenever you are accelerating, you have angular acceleration, torque is going to be positive. Whenever you have angular deceleration, meaning a negative angular acceleration, you're going to have a torque that it is negative. So that's the only way that we see the direction. So if this object was rotating like this, the torque would have to be applied opposite to the direction of the motion. That's why we have the negative, which means that the tangential force will not be applying tangential to the motion, or it will be tangential, but it will not be in favor of the motion, it will be opposing the motion. That's maybe you put in the finger, right? That's kind of the friction that it's decelerating the grinder wheel. So we see again another problem, very simple. We use this, let's see more examples. So in problem number 4, we have a man standing on a freely rotating platform. And here is a very important keyword because it's telling us that it is freely rotating, which means that we will understand this in a second. But let's remember it's freely rotating platform, right? So this platform, let's say, is rotating omega. So his arms are extended. And when his arms are extended, his rotational frequency, which is omega, so when the guy is with the arms like extended, let's make it long arms, and the rotational velocity is 0.25 revolutions per second, right? So of course we can directly convert 0.25 revolutions per second. 1 revolution is 2 pi, so that's going to be 0.25 times 2 pi radians per second, which means that's going to be, of course, 0.5 pi radians per second. And this is the initial situation. At the end, what he does is he takes and he draws them, I mean the arms, of course, and his frequency now, excuse me, is 0.8 revolutions per second. Ignoring friction, find the ratio of his moment of inertia in the first case to that in the second. So, what's the final scenario? Well, he's still here. And now he does this, he's upset. So then the velocity goes, angular velocity of course, increases, right? So that's going to be omega 0. So now the omega, final velocity is 0.8 revolutions per second. Let's write the 8. And we can convert again, that's 0.8 times 2 pi, which is 1.6 pi radians per second. Okay, very good. So now we ask, if the system is the man and the platform, we can remember that the change in, well, let's go step by step. So first of all, is this amount of motion changing when the guy is here or here? Well, here he has this velocity, the mass is the same, the mass is m. In the final scenario, the mass is still m, but the velocity has changed. So therefore, we know that the angular momentum has changed, right? It has gained amount of rotational motion. And that's kind of concerning, of course, or at that moment we say, why is he gaining angular momentum? Why is he gaining momentum? This is, I put this man on the platform, I just close my box, I wait the time, I open the box, and I see the guy spinning faster, and I say, how is this possible? Is he gaining amount of rotational motion? And I might be inclined to say yes, because the mass is the same as we are saying as the angular velocity is. But this is just a mistake. Why? Because this platform is isolated. It was telling us that in the problem, right? That's what we say, a man stands on a freely rotating platform and we are ignoring friction. So why is it possible the man is accelerating? Because indeed he is not gaining angular momentum. We say that the change in momentum is equal to the rotational impulse. And rotational impulse, of course, being the torque, so is times the time it applies. Is there any torque in here? No, there's none. There's no external influence. So then this needs to be 0. So the angular momentum cannot change. So we have to be careful and not just jump to conclusions. And why is that? Well, we see that because the angular momentum definition is not mass times mass times velocity, mass times omega, as we will do with the linear. This is not the case. Angular momentum is what? Angular momentum is inertia times omega. The velocity is in there, but we have to count for rotational inertia. And then rotational inertia, remember, it's given by mr squared typically. It might have some prefactors and some changes, but basically the idea is that you have indeed the mass, which is the same, but you also have how much or how is the mass distributed with respect to the axis of rotation, which the axis of rotation, well, you know what this is. The axis of rotation is just normal to, it's just in the center of the guy, right? So if that is the case, then as he brings the arms towards himself, he is reducing the radius, so he is increasing inertia. Let's see that. Let's see inertia initial, it's equal to the mass times the radius, whatever that is. So what is the question here? Find the ratio of his moment of inertia in the first case to that of the second. So what we can do, for instance, is let's calculate this. The initial momentum, let's call it sub zero, right? The initial angular momentum is what? Is the inertia initial times the velocity initial, omega sub zero. Well, we don't know how much is that inertia, but we do know that omega sub zero is 0.5 pi. What about the final? Well, the final is final inertia times final velocity, angular velocity, and that's going to be the the rotational inertia or the moment of inertia, final moment of inertia times 1.6 pi. And so we have said that the change in angular momentum is 0, which means that L minus L sub 0 is 0, which means that, of course, L is equal to L sub 0. Why is this relevant? Because based on that observation, I can say that the final and initial angular momentum are the same, and then I sub 0, 0.5 pi needs to be the same as I times 1.6 pi. Pi's and pi cancel, and what I can do is that the ratio of the initial, or let's do it the other way because it's much more comfortable. So the ratio of initial, let's do that, yes, let's write it maybe here. Ratio of initial to final, it's equal to what? 1.6 divided by 0.5, which is 3.2. So the question of why this object gained velocity, it gained velocity at the expense of what? At the expense of reducing its moment of inertia. The radius became smaller when he drew his arms towards himself, and the mass didn't change, but the geometry distribution did change. That means that the rotational inertia changed, means that the opposition to the momentum, to the rotational motion changed, and as a result of that, the velocity, the angular velocity increased. Why? To compensate for that, because again, what is conserved is the angular momentum. Why this? This is why angular momentum is an interesting variable, or is an interesting quantities, because it is conserved, and in this sort of scenario we see why. It accounts for both scenarios, for both situations. In the absence of any external interaction, the guy is gaining velocity because he cannot change the angular momentum, he cannot change the amount of motion. And originally, or at first, we might be tempted to say, it's gaining momentum because it's going faster, and it has the same mass as we would be saying in the case of linear momentum, which linear momentum is just mass times velocity. But that's because we're forgetting that mass is inertia in translational motion, but not just mass is the rotational inertia. Rotational inertia accounts for mass, but also for a geometrical distribution of that mass with respect to the axis of rotation of the object. So problems 5 to 7 in discussion are just kind of working in the same scenario. So let's analyze them all. We can start by reading the first one, which says that there is this construct where there is a central axis. So something like this, right? And there is at the base, there is a big plate, and then we have, well, this is what we have originally, right? It says there is a, a disk of moment of inertia I1, and is rotating freely with angular speed of omega sub 1. Let's assume it's just going this direction. It doesn't really matter, right? So that's supposed to be omega. Okay, very good. And then second non-rotating disk, we drop it with a moment of inertia I2. And then the two rotate as a unit. And we ask, what is going to be the total angular momentum, right? So this is rotating, and I'm going to drop on top. This is going to drop an object of I2 with omega 0. omega to 0, right? This is different from 0. So we have an object that is rotating, I drop another one that's not rotating, they have two different inertias, and then I'm going to pass to have this scenario, let's say, where I'm going to have this disk and I'm going to have the other disk. Oh, that's horrible. Let's see, something like this. Okay, and now they're going to be both moving as a single thing, right? Something like that, and both are rotating now with omega sub 3, and we're asking what's this omega sub 3. So it's a perfect scenario for conservation of angular momentum. Now, how we're going to solve this, as we solve everything, we're going to have initial and final, but the very important, the very first thing that we realize is, again, this. Change in momentum is equal to external impulse. Now, is there any impulse here? Are there any torques acting on the system? You may say this is hitting it downwards, but that's not relevant. We'll consider torque, which is tangential forces. So that means forces tangential to the circle. So there's none of those. So the torque here, the impulse here is going to be 0. So that means that the change in momentum is 0, which means that the initial minus final is 0, which means that the initial needs to be the same as the final. And this is exactly the same thing we've been solving all this time with problems in linear momentum, right? Okay, and then we want to find the angular velocity, so we're going to have to write the initial and the final. So let's calculate the initial angular momentum. We're going to have is a system made out of object number 1 and object number 2. That's going to be the total initial. And then we're going to have that the final, this is initial. Okay, if we use the sub 0, we don't need this. And the total final is just going to be L sub 3. Well, F sub 3 is the system composed by both, right? My system contains both. At the end, it needs to contain both. I contain both. I cannot just change the amount of, I cannot change the entities that contain or that contain in my system. They might be 1, 2, and then suddenly 3 or 4 or 5 or 6. Those things are not important. What matters is the amount. The same things, the same objects are in the beginning and the end, right? The same amount of stuff, so to speak. And then I can use conservation of momentum. So let's figure it out. How much is the initial? Well, it's going to be L sub 1 plus L sub 2, right? What is L sub 1? Well, L sub 1 is going to be I sub 1 times omega 1, and L sub 2, omega 1 sub 0 if you wish, doesn't matter, because we're calling this 3. That's why there's no ambiguity, right? So we could call it L sub 1, omega 1, excuse me. And then we're going to have plus I sub 2 times omega sub 2. And that's equal to what? That needs to be equal to L sub 3. L sub 3 is going to be inertia sub 3, we could say, and times omega 3. Good. Okay, so before we go ahead, what is this? L3 is inertia 3, right? Omega 3. Now, in the case of the masses, if these were two trains and there were two railroad cars, as we saw, and one was coming and they hit and they become one, what did we say in terms of inertia? That the inertias add together. Because if I want to move now this object, I don't only need to oppose or overcome the opposition of this disk. By moving this disk, I'm also moving this disk. So I need to account for the opposition of this plus the opposition of this, both together. And likewise, if I want to change this one, now they're connected, they're the same entity. To oppose the rotation of to change the rotation of this, I also need to change the rotation of this. So what I'm going to see is the inertia of 3 is actually the sum of inertia of 1 final plus inertia of 2 final as well. Now in this case, say initial or final for inertia is not relevant because we're not changing the geometry itself or of each one of these disks, right? It's like before that we were saying you extend the arms and you contract them. Here inertia is the same. So what is the inertia of 1? That's going to be the inertia of 3, excuse me, is I1 plus I2. So we can bring that thing here and write I1 omega 1 plus I2 omega 2, but omega 2 is 0, so that's 0. And that's equal to what? To I1 plus I2, which is omega 3, I3 times omega 3. So how much is omega 3? Omega 3 is going to be I1 omega divided by I1 plus I2 times omega 1. And that is the solution. So will it increase or decrease its velocity? Well, certainly it will decrease it. Why? Because this number is going to be always larger than I1. In the worst case scenario, I2 has 0 inertia, but 0 inertia means there's no mass. So it's going to be always larger than 0. So this number is going to be the number divided by itself plus a little bit at the very least. So it's always going to be smaller than 1, which means that the velocity of omega 3 is going to be smaller than omega 1. But it's important it's going to be always in the direction of omega 1, excuse me, because, well, we see it here in the formula, right? It cannot be otherwise we will not be able to compensate. So this is the equivalent we're saying. We have a railroad stationary, this comes here and they move with a slower velocity. we're seeing that. It was spinning and I dropped something and it's spinning more slowly. Why? Because it needs to conserve angular momentum. The amount of momentum, the amount of rotational motion that the disk had now needs to be distributed into more objects. Let's see problem number 6, which is a follow-up of this. Now in problem number 6, excuse me, we're going to still have the disk with a smaller one, and then we're going to have the larger disk, right? And then we're going to say, okay, and then what the problem says is that we are going to, a disk has a moment of inertia I1, and about the axis of rotation, what will be its new moment of inertia of a tiny mass m? We drop a tiny mass m on the disk, is set on it at the distance r of the center. So what's going to happen with the new rotational motion? So we have that. Even we can forget about this actually for the time being. This is irrelevant in this scenario. So let's say I have the disk and it's rotating. Sorry, it's rotating, right? And now I drop a small mass. So now I'm going to have the same disk, but now I'm going to add a mass. And the mass is going to be rotating with respect to the center with a distance of radius r. What's going on with inertia? Well, again, this is the same situation that we just explored. We're going to have the inertia of the object itself, but now instead of throwing a disk, I'm throwing a mass. But the problem is the same. Inertia increases. And how much is going to be the total inertial in that case is going to be the inertial of the disk at the beginning plus the inertia of the mass. And how much is the inertia of the mass? Well, there's a mass which is rotating with respect to the axis, so the equation that we know still applies nicely, which means it's just mass. In this case, the mass is m, so it's going to be what? Capital M times r squared, right? That's going to be that. So what's going to be the total inertia? Well, it's going to be the inertia of the disk, which if the disk, let's say, has a mass, I tell you that the inertia of a disk is equal to 1/2 mass of the disk times the radius of the disk. So if we assume that that's drop at the edge, then that's going to be 1/2 of the mass of the disk r squared, right, plus m r squared, right? That's assuming, of course, both have the same radius and you drop it exactly at the edge. So that's basically the idea. The idea here is inertias combined. So the total inertial is the addition of both of those, right? The point here, again, important is not this particular equation that may change with the geometry. What's important here is that to remember, if inertia is the opposition to the state to the change in the rotational motion, once that I'm rotating and I put more opposition, my rotation needs to change. But that's not because I'm applying an acceleration in this case, that's because I need to conserve the angular momentum. We are not having external torque. The angular momentum needs to be conserved. The only way to conserve that new angular momentum, remember, angular momentum is I omega. So if I'm changing the omega, if I'm changing, it's because I'm changing inertia. So inertia is additive. It's the same way as the mass. And in this case, to move now this disk with the mass, I need to move both disk and mass. So my total opposition to that motion is going to be the addition of both. If I try to think in terms of the mass, I'm going to move that mass, but it's not just simply moving that mass freely, but when I move that mass, I'm moving also the disk. So to move that, now I have the opposition of the mass itself plus the disk, and so on. Basically, the idea here is we need to combine inertias, we need to add them together. And now in problem 7, we're going to see a disk like the lower one in the problem above has an inertia of I1, and now they're giving us the value, which is 0.015 kilograms per meter squared, and it's turning at 3 revolutions per second. So let's say the omega is 3 revolutions per second, which means that every time we do a revolution is 2 pi, so that's going to be 6 pi radians per second. Very important always, do not forget, convert units to international system, always to avoid issues down the line. And then there's a trickle of sand, so let's make like a sack or something like that has a broken edge. And so from this sack, there's sand falling into there, right? Okay, then if it's a sack, we don't need to make it like this. It can be like a nice thing, like sugar or something like that, right? The package pierce a hole there and it starts to trickle down. And this is rotating. And since a trickle of sand falls onto the disk at the distance of the radius, it's telling you the distance of 20 centimeters, and immediately 20 centimeters, 0.2 meters, from the axis, and builds a 20 centimeters radius ring of sand on it. So at the end, I'm going to have a disk of sand on there. And it says how much sand must fall on the disk for it to slow to 2 revolutions per second. So the final velocity is going to be 2 revolutions per second, and that of course is 4 pi radians per second. Okay, and the question is how much mass needs to fall. So let's again remember, change in angular momentum is equal to the change is equal to the external impulse. Is there any rotational impulse acting in here? No, because there's no torque, there's no tangential force. I'm just dropping material, so this is 0, which means that the angular momentum change is 0, which means the initial needs to be equal to the final angular momentum. Now, why is it changing? Then let's write the initial and final momentum. What's the initial angular momentum? Well, it's just the initial momentum of the disk. And what is going to be the final? Right? The final is going to be, which we can just write here. That's the initial. What's going to be the final? The final is going to be the inertia of the disk at the end. So let's write 0. Plus the ring of sand. Let's write here sand. The angular momentum of the disk of sand. How much is this? This is going to be I sub 1 times omega sub 1 0. That's the inertia of the disk that doesn't change in time anyways. That's why we don't put the sub 0, but you could add it if you want. Times the velocity at the beginning, which is 6 pi. How much is the final angular momentum of the disk? That's going to be still the same inertia, but now the velocity is going to be something else. So we're going to be just calling it omega 1, right? Let's call this omega 1 and let's call this omega 1 sub 0. Initial velocity and final velocity. Plus the inertia angular momentum of the disk of sand. Now the sand is also rotating, making a disk. So how much is going to be that? The inertia of that disk times the omega of that disk. How much is the omega of that disk? Well, we immediately know that the omega of the disk is rotating with the same velocity as the disk 1. So that's going to be the same as omega 1, of course. It's not just rotating and the other thing is rotating slowly. They're both rotating together. So that's immediately something that we know. So let's start replacing numbers. So we have I sub 1 is 0.015. That's given by the problem, and that's going to be times 6 pi. And that's going to be equal to the inertia. The inertia is still going to be 0.015 for the disk. And now times omega 1. Omega 1 no, is not that one, is the final one, which is 4 pi, plus the inertia of the disk times the velocity of the disk omega 1. What's the omega 1? 4 pi. So we can just make these numbers, and we're going to see that we're going to have 0.015, 6 pi, minus 0.015, 4 pi, it's equal to 4 pi inertia of the disk. This is of course 2 pi times 0.015 and 4 pi times the E of disk. So what's going to happen is that the inertia of the disk is going to be equal to this divided by 4 pi, which is 1/2. So that's going to be 0.015 divided by 2, right? I could do it explicitly, but that's basically 4 pi, and that's going to be 2 pi. So the pi and pi cancels, right? So that's going to be 2 pi, and this is 2 times 2 pi, so 2 pi cancels, and then you have 0.05, which is 0.0075. And that's going to be the inertia of the disk of the disk of sand, right? Now the question is about how much mass is that. How do we figure out? Well, because we know the definition of the disk of inertia is going to be 1/2 of the mass radius of curvature, and radius of the axis, the distance to the axis. So let me erase here 1 second just to have some free space. And so we can replace that, and now we know that's going to be equal to what? Equal to 0.0075. And we can replace numbers in here. That's going to be 1/2 of the mass of the sand. This is what we will know. And the distance. The distance is 0.2 meters squared, and that's 0.075. So if you solve for the mass, you're going to find that this is there's a 0 missing there, 0.75. So you're going to have 2 multiplying that, it goes back to 0.05. So it's going to be 0.15 divided by 0.2 squared. 0.2 squared is, of course, 0.04. So that's going to be the same as 1.5 divided by 4. And that's 0.375, I think, right? Well, 0.35 kilograms. So what is the answer to the question, how much mass do you need to keep pouring to bring down the velocity? Well, 0.375 kilograms of sand. So again, we're saying in this case, that we add material, and by adding material, we are gaining inertia. By gaining inertia, we need to reduce the velocity, and that's what we are exactly observing. It will be a way of stopping down a wheel, right? How do you stop it? Just keep throwing stuff, right? But it's something that you're going to see anyways. If you're jumping in one of those kindergarten parks devices where people rotate, if you jump out of, the thing accelerates. Well, it's not, it accelerates because it gains velocity, but that's not because of any force acting in there. That's because it needs to conserve the total amount of momentum. And why is that? That might seem weird in that scenario, but it doesn't seem weird if I say I have a spinning toy, I leave it with no rotation, in an enclosed box, I open the box and I see it spinning. That will be weird. And so starting from that point, we say we don't expect that unless something external interacts. In this case, there's nothing external interact. Well, in the interaction will be this one, but that's part of the system, right? To see this, you have to imagine that at the beginning the disk is here. The system is not just simply the disk. The system is the disk and the sack of sand. And so this is my system. There's no velocity in here, so inertia times velocity here is going to be 0. So actually I could have here the sand before, right? The sand before it actually is poured. But the velocity of this one is going to be 0, so it doesn't really add anything. But my system was the sand and this. When I consider sand plus this, then it makes sense that conservation of momentum needs to be acting in here in the absence of a force. So that's why it's important to consider that your system includes everything at the beginning and at the end, even if this sack is dropping, because whatever is left in the bag is still contributing nothing because it's not rotating. So it's not contributing to the angular motion. The only thing that contributes to the angular motion is the thing that has fallen onto the disk. So once we make this picture, then it makes more sense. Yeah, angular momentum needs to be conserved because nothing external is interacting. And this is not external, this is internal in the system. It's just simply that before I pour it, it's not rotating, so it doesn't really have any amount of angular motion.